In this problem, we're going to analyze the motion of a rocket-powered cart. The cart is initially headed to the right toward a wall, and the rocket fires just as the cart hits the dotted line 100 meters from the wall. The cart then slows down, stops just before hitting the wall, and then speeds up off to the left. So the two main questions here are what's the minimum force required so the cart stops before hitting the wall? And secondly, how long does the cart take to return to its initial position? And one interesting point before we get started is that we're assuming the mass of the rocket and cart system is close to constant as a first approximation. Real rockets actually lose a lot of mass, and we're not going to incorporate that complication into this problem. So quickly reviewing the specs for this problem, this initial speed before the rocket fires is 50 meters per second headed toward that wall. The cart has a mass of 200 kilograms, and the rocket fires when the cart is 100 meters away from the wall. In part A, we're getting the minimum force exerted by that rocket so the cart doesn't hit the wall. And the way to tackle this problem is first to figure out the kinematics of it. What's the minimum leftward acceleration to make it so the cart reaches a velocity of 0 just as it gets to that wall? So this is what we want. V equals 0 at 100 meters. The initial velocity, 50 meters per second at that initial position, which we're going to call 0. And then our final position to reach that velocity of 0 is 100 meters. And the time-independent constant acceleration kinematics equation, v squared equals v naught squared plus 2a times the displacement, x minus x naught, is very convenient here. I plug in my final velocity of 0. My initial was 50. I know my final and initial positions. The only unknown there is the acceleration. And when I run the numbers on this, I get negative 12.5 meters per second squared. Again, that's a negative because it points to the left. Now we want to figure out the force exerted by the rocket corresponding to this minimum acceleration to stop before hitting the wall. And this is just given by Newton's second law. We know the force is related to the mass and acceleration of the cart by F net equals ma. And the net force in the horizontal direction, well, there's only one force in the horizontal direction, and it's the force exerted by the rocket. So we plug in the mass of the cart, 200 kilograms, and we're just going to work in magnitudes here. The magnitude of the acceleration that we just got was 12.5 meters per second squared. And when we run the numbers on this, we get 2,500 newtons for this minimum force for the cart to stop before it hits the wall. In part B, we want to get the total time it takes the cart to return to its initial position 100 meters from the wall, right when the rocket began to fire. So we have a constant acceleration for the entire process. It's negative 12.5 meters per second squared. And our initial position for this is 0, and our final position is 0. So we're looking at the entire round trip with this cart turning around and coming back to where it started. Of course, we also know the initial velocity was 50 meters per second. And it's the time that we're looking for. So we use our first kinematics equation for this. That's x equals x naught plus v naught t plus 1/2 at squared. We plug in that our initial and final positions are both 0. And then we'll go ahead and plug in the numbers, and I get 0 equals 50t minus a 1/2 times 12.5. I just moved the minus sign from the acceleration out in front of that term, times t squared. Now this is a factorable quadratic equation, so I can pull one factor of t out of it, and I get 0 equals t times 50 minus, and then half of 12.5 is 6.25, so minus 6.25t. And anytime you have two factors equal to 0, you get a solution when either one of those factors is equal to 0. So one of the solutions is t equals 0. And this makes sense because that's one of the times where the position of the cart is 0. But it's not the time we're interested in. We're interested in setting the other factor equal to 0. So we set 50 minus 6.25t equal to 0. And when we solve for t here, we get exactly 8 seconds. So it takes exactly 8 seconds for this cart to slow down as it approaches the wall, turn around and get back to where it started, and we're done with the problem. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.